In order to even discuss fluids and fluid therapies, it's imperative that we're talking the same language. And for that reason, we must cover some basic chemistry concepts. I previously introduced atoms and molecules, the periodic table, atomic mass, and molecular mass. This time we will visit the concept of moles and molarity. From there we will be able to explore the concentrations in millimoles per litre and grams percent. Tutorial 1, Water and Concentrations. This time I will discuss the basic physical properties of water, how and why moles determine quantity, and how to figure out the alcohol-calorie content of a drink. Terminology. In chemistry, the quantity of a substance is calculated in moles. Traditionally, 1 mole equals 1 gram times the molecular weight or the molecular mass. It contains 6 times 10 to the power of 23 particles, and this is known as Avogadro's number. That is the official 2019 definition of a mole. It is more precise than that, but that's what you need to remember. So when we're talking about quantity here, we are going to be talking about moles. If I have 1 litre of water, how many moles does it contain? Remember, the molecular mass of water is 18, and 1 mole is 1 gram times the molecular mass. 1 mole is 18 grams. 1 kilogram is 1,000 grams, or 1 litre. 1,000 divided by 18 is 55.55 moles. Water attracts water. It's polarized. It has 2 different poles, a negatively charged pole and a positively charged pole, and they kind of stick to each other. So different molecules of water stick to each other and clump together, and that's why we have life on this planet. So these water molecules form electrostatic bonds between each other. This forms rain, it forms the sea, it forms raindrops. Now, water is a substance that breaks up other substances, so anything else that's held together by these electrostatic bonds will dissociate into their component ions when they dissolve in water. It's a strongly ionizing solvent. This is particularly important with respect to salts. When a substance is dissolved in water, we can measure its concentration in millimoles per litre. So here are 2 different substances that we will frequently dissolve in water: glucose and salt. So when we put in glucose into water, water just dissolves in the glucose, so it breaks down and then it disperses. So in this situation we may have glucose at 5 millimoles per litre. Salt crystals dissociate first, so they break up into their constituent parts, and then they dissolve and disperse through the system. So in this situation, we start off with NaCl, and now we have a specific number of millimoles of sodium and chloride. Understanding concentrations. You're called to the emergency department. Emma is a 19-year-old diabetic, and she arrives to the ED confused, and then she becomes comatose. When the blood sugar is measured here, her glucose is 2.8 millimoles per litre, or 50 milligrams per deciliter. You were told to give her 50 mils of 50% dextrose. So 5% or 50% dextrose, you'll hear these different fluid types quite frequently. What exactly does grams percent mean? Grams percent is the number of grams per 100 mils. Percent, 1 of 100. 5% dextrose is 5 grams per 100 mils. Scaling that up to a litre, that's 50 grams per litre. And because each gram of glucose or D-glucose dextrose contains 4 kilocalories, that works out at 200 kilocalories per litre. If you wanted to make dextrose, you'd take a litre of sterile water and then pour in 50 grams of dextrose powder, mix it all up, and there you have it, 5% dextrose. What is the molality of 5% dextrose? Well, the first thing you need to do is calculate the molecular weight of glucose, and the chemical formula for glucose is C6H12O6. C6 is 12 by 6, 72. H is 1, of course, so it's 12 times 1, and O6 is 16 by 6, and that is 96. So 72 plus 12 plus 96 is 180. That is the molecular mass of glucose. 5% dextrose is 5 grams of glucose per 100 mils, or 50 grams per liter. 1 mole is 180 grams. 1 millimole is 0.18 grams. 1 gram is 5.4 millimoles. 50 grams, therefore, is 278 millimoles. So 5% dextrose contains 278 millimoles per liter. And as we will learn later, it also contains 278 milliosmoles per liter, i.e. it is isoosmolar with plasma. If I infuse 1,000 mils of dextrose into Emma intravenously, how much does her body water increase? A, less than 1,000 mils, B, 1,000 mils, or C, greater than 1,000 mils? The correct answer here is actually C, more than 1,000 mils. Because when 5% dextrose is injected into the body, within 15 minutes the sugar is taken up by cells and metabolized to carbon dioxide and water. Each 278 millimoles of glucose results in the production of 1,668 millimoles of water, which is another 30 mils. Whoa! How did I calculate this? 1,000 mils of water, as we've already discovered, contains 55.56 moles. 1 mil contains 55.6 millimoles. 1,668 divided by 555.6 equals 30 mils. How much glucose do you have in your extracellular space, assuming that the volume is 15 liters? Normal blood glucose is approximately 5.5 millimoles per liter, and 1 millimole is 0.018 grams, or 180 milligrams. 5.5 millimoles per liter, therefore, is 99 milligrams per deciliter, or approximately 1 gram per liter. If the extracellular fluid volume is approximately 15 liters, that works out at 15 grams, or about 1 tablespoon of sugar. If we give Emma 50 mils of 50% dextrose, or D-glucose, that's 50 grams per 100 mils, Emma receives 25 grams of dextrose. 25 grams is 138 millimoles, or 100 calories, 1.66 tablespoons of sugar, or about 2 millimoles per kilogram of body weight, assuming that she's about 70 kilograms. There's no 50% dextrose available. Do we have an alternative? Well, of course we have. Any glucose-containing fluid is an alternative. So if 50 mils of 50% dextrose is 25 grams, that's 138 millimoles of glucose. We can give 250 mils of 10% dextrose, 25 grams, 138 millimoles, or 500 mils of 5% dextrose, 25 grams, or 138 millimoles. One of the strange and confusing things about the world we live in is different parts of the world use different ways of measuring quantity. In most of the world these days, millimoles per liter is what is used for measuring quantity on blood tests, but certain places, particularly in North America, the United States, use milligrams per deciliter. So just imagine Emma is a diabetic. After receiving 50% dextrose, you check her blood glucose with the strip machine and you get this result: 103 milligrams per deciliter. And if you, like me, are European and you are unfamiliar with milligrams per deciliter, how do you figure out what her blood glucose is in millimoles per liter? Well, let's work the problem. Emma's blood glucose is 103 milligrams per deciliter. The molecular mass of glucose is 180. 1 mole is 180 grams. 1 millimole is 18 milligrams. 103 divided by 18 is 5.7 millimoles per liter. So this is easy peasy. Part 3. Let's talk about booze. When we talk about alcohol, we're really referring to ethanol, and that has a chemical formula of C2H5OH. Going back to the periodic table, here is atomic number 1, hydrogen, which has an atomic mass of 1.01. Element number 8 is oxygen with an atomic mass of 16. And element number 6 is carbon with an atomic mass of 12. So 2 by 12, 6 by 1, and 16 is 46.065 grams per mole. That is the molecular mass of ethanol. 1 gram of ethanol contains 22 millimoles, or 1,000 divided by 46.05. And just as an aside, there are 7 kilocalories per gram of alcohol. You order a pint of beer, and where I come from, a pint of beer is 568 mils, and that's 5% alcohol. How many millimoles of alcohol and kilocalories does it contain? The molecular mass of ethanol is 46.05. 1 mole is 1 gram times the molecular mass, so 1 mole is 46.05 grams. 568 mils at 5% is 5 grams per 100 mils, or 28.4 grams. 28.4 divided by 46.05 is 616 millimoles. So there are 616 millimoles of ethanol in my pint of beer. Because there are 7 kilocalories per gram, 28.4 grams times 7 is 200 kilocalories. These are just some different drinks that you might encounter. A beer, which is 5% or somewhere in that range, alcohol, wine around 13%, and vodka 40%. This is alcohol by volume. Sometimes you'll see this term proof for referring to alcohol, and proof is twice the alcohol by volume. So if you have a beer, there's 5 grams per 100 mils, or 28.4 grams for 568 mils. That's an imperial pint. 200 calories, or 0.6 moles of ethanol. Wine is 13 grams per 100 mils. A standard glass is about that size. 91 kilocalories, or 0.03 moles of alcohol. Vodka is 40 grams per 100 mils, or 16 grams in 40 mils, which is the standard shot of a spirit. That works out at 112 kilocalories, or 0.035 moles of ethanol. Johnny is stopped by the police for suspected drink driving. His blood alcohol is 20 millimoles per litre. The legal limit is 0.08%. Is Johnny over the limit? Let's work the problem. In the USA and the UK, the legal limit is 0.08% ethanol per 100 grams. In Europe, it is 0.05%. 0.08% is 0.8 grams per 1,000 mils. 0.05% is 0.5 grams per 1,000 mils. 1 mole is 46.05 grams, so 8 divided by 46.05 is 17.3 millimoles. 5 divided by 46.05 is 11 millimoles. So Johnny, at 20 millimoles per litre, is drunk on both sides of the Atlantic. In this tutorial, I cover the basic physical properties of water, the concept of the mole and molality, the different ways concentrations are represented in terms of milligrams per deciliter, grams per litre, and grams percent, and finally how to convert grams percent to millimoles per litre. Next time, I will discuss how to calculate the number of millimoles of each component of a compound dissolved in water. Okay, so that was a discussion on water and concentrations. You can move on to the next tutorial if you wish, or wait and follow with the first supplementary tutorial on caffeine and local anesthetics.